I'm Gabriel Martin, I'm a physicist, and what I want to introduce today is a novel approach in order to optimize progressive lens design. The algorithm is based on one of the artificial intelligence approach. We will see now which one is it. Okay, but to start, we need to mention the evolution. And why we are measuring to the evolution? Because the evolution, natural evolution, is a very efficient technique in order to optimize different individuals to be adapted to the environment. The adaptation process is based on mainly in two different approaches. One is the crossover and the other the mutation. So the relationship between the biological evolution and a progressive lens is that in both cases are complex problems, and what is possible to do is work with genetic algorithms in order to optimize the surface. And is that what we really made? In 2015, we developed the continuum design technology. It basically is about calculate the error on the whole surface of the lens, taking into account infinite points and discarding the problem of interpolation. And this is a schematic equation about the optical error. What that means is that I have mainly two terms, one and second. This term is about power. So this is the difference point to point between the power, the target power, and the power that the lens has. And this is the same for the astigmatism. It's the target astigmatism minus the astigmatism that the lens has in one specific point. If I zoom point to point on over all the solid surface, what I have is a total error. But as you know, it's not possible to have a progressive lens without aberrations. So once that we establish a math, or any company in the market establish a math, what is necessary to do is to define a couple of functions that are the functions that we use to communicate with the math in order to tell about where are the designer more interested in have low aberration or the power be constant or whatever. So, summarizing, we are not able to create lenses without aberrations, but we need some kind of functions to tell to the math what part of the lens is more important for us, okay? And we do that through these two functions, alpha and beta. So this is a typical map from a standard progressive lens. What you see in dark blue is all the area of the lens where the aberration is lower than half diopter. And you have the progression here in the channel. This is near vision. And this represents a typical alpha or beta function. In this case, it's a matrix. And when you see red here, means that for me, for the designer, is more important the area. So the number there will be higher. And in this part, it really doesn't matter to me because maybe this is outside the frame. So the math can relax there and put the aberration in this area, okay? So this alpha and beta function are characterize the design, are the DNA of the lens. So if we have one specific mathematical model, just by changing alpha and beta function, we create different models, okay? More open, closer, or whatever. So this is, suppose that we have an alpha and beta matrix, and we work in the discrete instead of the continuum. So I have different numbers in each of these squares. If the number is higher, that part is more important. If it's lower, it's less important, okay? So what we can do is put two matrices together in this arrangement and start to move from left to right and from here to bottom, so to down. And then what we have at the end, if we do this, okay, we transform two two-dimensional matrix with 3,200 elements, for example, to only one string. Okay? So we change the matrix to represent only one string. And why I want to do that? Well, I want to do that because this is the DNA of my lens. This is the DNA of my design, because this chain characterizes the design itself. Each of these numbers are there, okay, are the chain. And I can write in the binary mode, so I have a DNA with two bases, 0 and 1. And this is what happened in the real life, where the chain are made by 4 different bases, and the DNA is double. It's not just only chain, but it's double. So this is the analogy between our approach. So how can we characterize the DNA of a progressive lens, one specific model, and this is how the nature works. So what I introduced before was the genotype of a lens, the genoma, the genetic information. But also in the nature, we have the phenotype. What the phenotype is what we can see. The phenotype in the human being is defined by the color of the eye, the skin, or some other characteristic, okay? Is what is expressed. In the lens, in the progressive lens, the phenotype is, for example, the map, or are the maps. Are the maps for aberrations, are maps for mean power. Because this is what I can observe in the lens. I can map one lens, I can map another lens, different design, and I can see the phenotype that are the maps, okay? The maps can be measured or can be calculated using Gauss equations. So in 2018, we start to work in this project. The name was R2-D2 because it's the robot of Star Wars. The idea was to create an algorithm to create the functions alpha and beta in some way that in unsupervised way. So in some way that no human being be involved in the process. That is really important because it's optimized and can obtain designs where the aberrations are lower than the aberrations that I can get just putting myself, for example, the numbers on alpha and beta functions. Okay, but just like nature does, there is, you know that the nature rewards or punish to the individual. Individual that is best, there are individuals that are good adapted to the environment and others that are not. So in some way in our toy model, we need to define a metric in order to say if one specific individual is good, is so-so, or is bad. And that is made by the fitness function. The fitness function is a function, is a number, basically. It's an equation that I have a map, I have a progressive lens, and apply this function, and I obtain a number. If the number is higher, the design is better. If it's lower, the design is worse, okay? And take into account different areas of the lens. far vision, the corridor, near vision, and here the periphery. This approach is interesting because at the beginning we have alpha and beta functions that need to be modified by the designer, and it has thousands of elements in total. But now what the designer needs to do is only to define the fitness function. And the fitness function only uses 10 or even less than 10 parameters. So the original problem had thousands of degrees of freedom, and the problem now have only less than 10 degrees of freedom. That is a very, very good advantage. Another advantage is when I say that one specific design is good in far vision, the red area that I'm showing here, that means that it's good in both astigmatism and power. Because as you know, when you move from the center to the periphery in a progressive lens, the power increased, became positive. And this is a problem because many times the patient see blur, but the blur is not because the aberration, but it's because it's the power, positive power. And the tolerance is 0.25. Tolerance is half of a tolerance for astigmatism. Tolerance for astigmatism is 0.5 and 0.25 for power. So when I say if one specific design is good or is not in far vision, is because are fulfilled both conditions at the same time. That is the advantage. So let me explain how the crossover works. As you know, in the nature, the crossover is we have two parents and they exchange genetic information, right? So the child has genetic information from father and mother, correct? Something like this is what we do. We have, suppose that this is the genome of one specific design, and this is the genome of another design, different to this, okay? Take into account that this represents alpha and beta function, and alpha and beta function can to define the design. So this is one, and this is other design, okay? So what we do is, for one specific gene, for example, this or this, we have a DNA for the child in the center, and suppose that this is a binary number that represents the value of this square, and this is the binary number that represents the value in this square. So suppose that in that case, in 10 base is 488, and this is 185, okay? This is in binary, and it's in binary. So these are representing the same gene for the child. So the child receives genetic information from parent 1 and parent 2. How much received from parent 1 and parent 2 depending on fitness score. If one parent was better than other, so we apply a higher probability to give the genetic information to the child. Otherwise, we reduce that. In that case, we are assuming that in both, for both parents, the fitness score was almost same, and then both are given the same amount of genetic information to the child. So in this case, the gene for the child is 425. And we also have the mutation. You know that the mutation happens in nature. The reason for the mutation can be radiation, and sometimes are error copying the DNA. During the COVID time, we heard and watching the TV many times about mutation, the evolution of virus, and blah, blah, blah. As you know, mutation happens, and that is switch one value in one gene for another, just by chance, okay? So in this kind of algorithm, it's necessary to apply the mutation because it guarantees explore a bigger, larger area of interest in all the solution C's. So, for example, if the mutation is just switch this 0 from this 1 to 1 in this part, but keeping the rest of the number the same value, so I modify from 465 to 56 to 458 in decimal. Due to it's not the same to do the switch this number than this number or this number because it has a different consequence, is that the probability of the mutation that we apply depends of the position of the number. So if it's represented by this triangle. So it's more probably that we have a mutation here than in the middle than in the top of the chain. So how the algorithm works? We define an initial population. The initial population is, I have many designs and put all designs together. I'll calculate the phenotype. Phenotype means calculate the aberration maps and mean power map, okay? We apply the Gauss equations, forms 1 and 2, in order to calculate the power and astigmatism. Then we make that the design cross one each other, so exchange genetic information. That means that the alpha and beta function cross, following the rules that I explained. Then, Then we apply the mutation. And then we have a new population. The new population has the parents and the child, the offsprings. So what I do is calculate the fitness score and say, okay, which one are the best ones? Okay, I keep this set. And worst ones we kill and remove from the population. So I have a new population now that was better than the first one. So I am here in this point, and then this is my new initial population. And I repeat the algorithm once again, and once again, and once again. Using very powerful computers that we rent in the cloud, we can run this for many days, and at the end, what we have is that the population is all very, very homogeneous. That means that the most of individuals have the same genetic information. That means that the alpha and beta function are almost same. So the distribution from mean power and from astigmatism is almost same. This is a short video trying to explain a very high level how the algorithm works. So this is a parent 1 and parent 2. We calculate the score, crossover, have a child. Calculate the score for the child. If it's good, we keep it. So the child now in the second generation have the crossover with a different design, and the offspring was bad because the score was lower. So we kill it. If we do that for many, many, many generations, at the end what we have is that the final individual is optimized following the fitness score that we define. That at the end is the criteria that we use to say if the lens is good or is not. So this is a real example, it's not Photoshop. That belongs to, is an aberration map for the lens addition 2, a minimum fitting height of 18. So this is a standard lens. It's in temporal side, we got 2 diopters and 2.1 in nasal. And this is one of the results for the evolutionary algorithm. That is 1.75 in nasal area. That normally is higher because everything is compressed. And 1.35 here in the temporal side. I don't know if it's clear. Maybe it's too bright here in the room. And if we see with the detail, you will see that the field of view of this lens almost keep the same that the digital lens that I have in the left, but the algorithm was strong enough to reduce the peripheral aberrations. So, and that is the idea what we want to do. Speaking about the performance, this is a real mapping of the lens, MFH 18, addition 2. These maps correspond to the Rolex mapper, are made in Israel, and these belong to one very famous design in the market. As you can see, the aberrations for this one is much better than for the islands. Much higher, sorry, not much better, but much higher. This is 2 diopters. This starts in 2 diopters, so this is higher than 2, and this never reached 2 diopters. So, at the end, what we try to do is improve the performance, and the performance is to get a better adaptation, decrease the swim effect, optimize the vision field, very good spatial perception, and has a natural vision. And all this depends of how stable the mean power is horizontally, and also depends of aberrations. And so that is the problem that we try to fix or optimize, and we are happy because we think that we make a very, very good improvement. So that is all. So it's a very short talk. I don't know if you have any question. Let me know. Thank you.